Okay, so let's start. Good morning or evening, everyone. Depends where you are. You're going to do a presentation about ASCOT5 with Konsta and Mathieu. Konsta, go ahead. Start.
Yeah, thanks, Mathieu. Yeah, so hi, everyone. So as we introduced yesterday, I'm Konsta. I'm the lead developer of ASCOT5, and Mathieu is the expert that ported ASCOT to the GPUs. So I thought the summaries will be, or the summary of this presentation and the ASCOT task. So ASCOT5 is a plasma physics code, and it's used by physicists and engineers, and it is used to develop fusion energy. And this field of fusion energy as a whole, it strongly relies on modeling. So we have a lot of different models and high performance. Most of them are HPC codes, and I'm saying this because ASCOT is solving a very specific issue in this whole picture. So there is not a single code that would solve the whole reactor or the whole plasma, how it behaves. But every code has this single or small purpose, what they're doing. And what ASCOT is doing in practice, it solves the trajectories of the plasma particles, and it does so by assuming that there are no interactions between the simulated particles. This is an important assumption because, well, from our point of view in this presentation, this means that we can simulate each marker in parallel, and this is where the optimization in ASCOT is basically based on, that we try to simulate markers or parallelize the code as much as possible. And this code is optimized both for the CPUs and the GPUs, and it's a hybrid code. So for the CPUs, we used MPI plus OpenMP, and for the GPU, we have the option to use the MPI plus OpenMP or OpenACC. But I will discuss this more in detail later. And your task is kind of like practical or interesting, at least from my point of view, because you will be simulating a real tokamak or real fusion reactor or experiment that will begin operating in the next year, and it has this goal of producing 140 megawatts of fusion power. So I will cover each of these topics in detail now, but I will begin with the physics basics. So I'm not sure how many of you are physicists or know a lot about nuclear fusion, but I will cover those. So this nuclear fusion, you might have seen this picture on the left, that you have light elements that fuse together, and then they release heavier elements and neutrons, and then this binding energy is then, or extra binding energy is then converted to kinetic energy or thermal energy, and then that's how you gain energy from fusion. And then the fusion, as you might have heard, basically it's a endless or very abundant energy source, and it's clean and so on. It doesn't produce carbon dioxide. So there's your reason that why we are pursuing this. But if you don't care about the environment, then there is I like this approach that is in this video game Civilization 5, that if you develop nuclear fusion, then you gain access to these giant death robots, and who wouldn't want to have those? And this nuclear fusion, it's a difficult process, and it has been tried since 1930s at least. And where we have a working fusion reactor is in the sky. So sun and other stars, they produce their energy with this nuclear fusion process. And why it is so difficult is that it requires high temperatures, and you also have to have when you have high temperature, the particles are moving faster, but you have to keep them confined so that you can actually have enough reactions producing the fusion. And the specific reaction that we are currently pursuing at the moment, it requires a temperature that is at least 10 times the temperature that is in the sun's core. So that's quite a lot of quite high temperature. So something like 10 million degrees Celsius. And in this at these temperatures, all the matter becomes plasma. So you have this problem that this plasma cannot touch any material surface, or otherwise the plasma would either cool down or the material surface would melt. So that's the main issue. And this is why the most successful fusion energy production has been in this uncontrolled manner, or this man-made fusion, so in the hydrogen bombs. But we don't want to use those for energy production. So nowadays there are two main ways of producing fusion. So this third picture, it's this laser facility in US. So this is the other main route, and there you have this. If you look at this pencil-shaped target there, so at the tip of the pencil there is a target that is like size of your tip of your finger that contains the fuel, and then all of these ports on the wall, they are laser beams that are then focused on this small target, and then they compress the target and make it implode, and that produces some fusion energy, and then you put a new capsule and again make it implode and so on. But I won't be talking about that anymore, because ASCOT is not for that, but instead ASCOT is used in this magnetic confined fusion. So this last picture shows the internal of a magnetic control device. And there we use strong magnetic fields to keep the plasma from interacting the reactor or touching the reactor walls. So this is the basis of the magnetic confinement. So plasma, it's defined, or what plasma looks like is that it's basically gas, but there you have electrons and ions that are moving freely. So it's a like charged gas, or not. It doesn't have an electric charge, but the electric charges can move around freely. So it means that it responds to electromagnetic fields, and actually in turn it then also generates electromagnetic fields. So what happens is that if you apply a strong magnetic field, then if you remember from your elementary physics courses, then the particles start gyrating around the magnetic field. So they can move freely along the magnetic field, but then the movement across the field is strongly reduced. And this is the basis of the magnetic confinement, that we create some kind of magnetic field that when the particles are just tracing this single field line, then they stay confined and the plasma stays confined. And in the right hand, I have this figure or schematic of a very early fusion experiment from the 30s or something. And there the idea was that we would have this kind of machine that these green lines are the magnetic fields, and the plasma would be confined within these, and then we have this phenomenon called magnetic mirrors at the end. So the plasma would be confined here. But then the problem was that these magnetic mirrors are not perfect. So we got, or they got losses from these endpoints of the magnetic field. So the obvious solution, of course, is to just wrap the field around like a donut. And that's actually what we are currently doing. So in this magnetic confinement, there are other different variations of how we could pursue those, but these are the two main routes. So this tokamak device and then this stellarator type device. And how they work. So in this tokamak device, this purple is the plasma, and then these blue D-shaped coils, they are huge magnets, and they create this kind of toroidal field that goes around the torus. But that's not sufficient to confine the plasma, but you also need this boloidal field that goes like these circles around the plasma in this main radius. And this is generated by driving current through the plasma. And this current is driven by the central solenoid. And that's the tokamak way. And then the other way is to have the stellarator, and how it differs that here we don't have plasma current, but instead the whole magnetic field is generated by the magnetic coils themselves. So here the yellow is the plasma, and then these blue stuff here are the coils. And these have their drawbacks and advantages. So for the tokamak, the drawback is that to drive the current, you have to drive electric current through to the central coil. So you have an increase in current there, but because you cannot increase the current indefinitely, but sometimes you hit a maximum at some point, which means that this tokamak is like a pulsed operation, so that you drive your current and then you stop and then you drive another pulse. And other issue with these tokamaks is that due to this plasma current, I'm not going into details, they are prone to instabilities. But with stellarators, because we don't have the plasma current at all, they are steady state and they are not so prone to the instabilities. But then the problem is that, as you can see from these magnets, that it has more complicated design. And so far, the tokamaks have performed better historically, and this means that these stellarators, they have been less studied, but this might change in the near future. But your test case and rest of this talk, I will be focusing on the tokamaks, because this is the like the main route still. So you always, at least in this field, you hear the question that when the fusion is coming. So I will try to give some, not an answer, but at least say that where we are at the moment. So current record for fusion production is that in the UK in the 2023, so just a couple of years ago, 10 megawatts of fusion power was produced for 6 seconds. But anyway, but then if you look at the numbers that for our actual power plant, we would need hundreds or 1,000 or more megawatts of fusion power. So we are still far from that. And then there is this another important figure of merit is this fusion energy gain factor. It's not really the like energy returned on or for energy invested, but it's more like that. It's a more physics-based merit, but it means that for a power plant you would need something like Q equals 30 or 50 that is needed. And right now we are still below 1 in this Q. But then the next, I would say, milestone is this ITER project, which is being built in France. And this has the first plasma coming planned for 2034. And it is going to produce some reasonable values of fusion energy, so 500 megawatts. And it tries to achieve Q equals 10. So it would be actually net producing power. And then there are, this is not the only experiments, but there are dozens of public experiments worldwide that are providing support for this ITER, and more are planned also. But then in the and here are some scales that how large machine this ITER is. So there's an aerial view of the ITER site. So this whole complex is this just for this ITER project, and the ITER is located in this black building here in the center. And here's it's not quite up to date, but I think this picture is from the last year from the actual tokamak. So there are no people standing around, but this orange box here in the lower right corner, for example, that's about the size of a human. So it's a huge machine. But in the recent years, also the private sector has gained interest for the fusion, and the problem with the ITER is that it has been planned and it has been being built for several decades already. So it's based on, let's say, a bit of old technology. But then these private enterprises, they can take advantage of the advantages that have been made in the magnets and in the computational power. So they can try different strategies. So one that I would like to highlight is this Spark experiment that is by Commonwealth Fusion Systems. There are others, but we have been working with these with ASCOT. And your test case is from this Spark reactor. And this, as I said, it's planned to begin operation in the next year. And the plan is to have fusion energy production of 140 megawatts. And something, I'm not sure if they have exact goal for the Q value, but at least 1, maybe 2, maybe even 10, but we will see. And they are based on solid science, but what they have is that they have these better magnets, so they using more recent superconducting magnet technology. So if you compare the numbers ITER versus spark, so the plasma volume ITER is much larger, but on the other hand, the magnetic field, which the stronger magnetic field you have, the better confinement, the better you can confine the plasma. So if you compare those, then the spark has, due to the technology, has higher magnetic field. But ITER is not just testing the fusion itself, but it's testing other processes like the breathing of the tritium fuel and so on. But I still like to mention that these both are still experiments, so they are not producing electricity. So these are just prototypes, and then after these we will be trying to build a actual first fusion power plant. Yeah, and then let's get back to ASCOT and how to model plasmas. So as I said, plasma is gas where the charges can move freely, and it's very interesting because if you think the plasma, it's just, you can just think that it's like billiard balls. Other balls are massive and have positive charge, and then you have these tiny balls that are negatively charged, and then you can basically model them using classical mechanics just. So it's in principle, it's a very simple system, but due to the electromagnetic force being a long-range force, and then these charged particles generating electromagnetic fields and responding to those, then the plasma is actually very complicated systems, and it's not easy to model at all. So it's much harder than ordinary gas. And there are different ways that this problem is approached. One main route is the fluid model. So we just model the plasma as a fluid. But this simplifies the problem a lot, and we lose a lot of physics that is happening in the velocity space, because as a fluid you assume that all particles are flowing with the same speed. And then the other approach would be to model the particles as single particles. So you just take your Lorentz force and then see that the plasma particles are gyrating around the magnetic field and so on. But looking at just single particles, you lose this collective behavior that the plasmas exhibit. So you cannot, that cannot capture the whole plasma. So the only model that can capture the whole plasma physics is the kinetic theory, where you just model the plasma as using distribution function and assuming that it consists like this probability distribution, and then consisting of large number of particles. But this is very difficult and computationally expensive approach. So there are different kinetic models that try to simplify the problem a bit. But all of these models have their place. And as I said in the beginning, we have several codes in the plasma physics, and some are based on the fluid model and some are based on the kinetic theory, and they work all together. And some codes even might combine these models. For example, ASCOT. ASCOT is like a combination of the single particle and kinetic code. So what we are doing with ASCOT is that, well, if you have, maybe some of you have heard the Monte Carlo code. So that is in principle what ASCOT is, except that ASCOT is not doing any random sampling, so I don't like to use the Monte Carlo. But ASCOT is modeling a large number of single particles, just following individual particles. And as you follow a large number of those, and each of these particles markers are representing a huge number of physical particles, you're essentially modeling the whole particle population. And ASCOT is first principle based, so we don't have any tunable values in the physics, so everything is based in the first principles. Of course, we have values that you can adjust, like time step and so on, but like you cannot adjust the strength of the interactions or anything like that. And we have further assumptions in the ASCOT that there are no interactions between the simulated markers, and also the markers, they don't give any feedback to the background. So I'm not saying that the backgrounds have to be static, they can be time evolving, but there cannot be any feedback from the markers, because the markers, they also generate electromagnetic fields, but these are not accounted in the simulation. So this means that the ASCOT cannot solve the whole plasma, but more it can solve like minority particles population in the plasma, that you can think that they are just like perturbations in the whole picture. But the benefit of ASCOT approach is that we can incorporate complicated geometry, so we can have any kind of magnetic field perturbations because they are not ever perfect. They have some issues, and then some are intentionally introduced. And then one is that the reactor is going to have 3D wall, and that's also an important thing that ASCOT can take into account. I will show later some figures. Yeah, sorry. Just showing here, so the picture, what ASCOT is in principle doing is that this black line here is the wall, and then we are just tracing, this blue line is one marker that hit the wall. But we are tracing these particles, and that's what ASCOT is doing. Simple. Okay. And as for the code itself, so you have noticed that it's ASCOT5, so it's the 5th incarnation of ASCOT line of codes. The first original ASCOTs, they were written in Fortran, and some used MATLAB in post-processing. But how this new version differs from the previous ones is that this is the first one that is actually designed for high-performance computing. And this one is written in C, and pre- and post-processing is in Python. But in the future, I will try to have it so to make it the proper code like NumPy, so that you would have C library that is fully interfaced with Python, so that the users will only interact with Python. And this code is available in GitHub, so it's an open source code. And then you can also visit the GitHub page and then look for the link there, and you can find where is the online documentation. It also gives some installation instructions if you need them, and tutorials if you're interested. You don't need those for this task, but if you're interested, you can look. Yeah. And yeah, as for the users and the applications, well, ASCOT has a wide range of use cases because almost all fusion devices, they have fast particles, because if you have fusion happening, then you have these fast helium products that are generated by the fusion, and ASCOT is used to model those, or can be used to model those. And actually studying their confinement is the bread and butter of ASCOT5. ASCOT is widely used in the universities and scientific institutions and also companies. So I would go so far as to say that if fusion is the technical and scientific feasibility of fusion is demonstrated within 10 years, then it's very likely that ASCOT was involved in somehow in this process. And because it's open source, it's very hard to estimate the number of users, but just trying to give some rough estimates, I think there are some dozens of publications that have used ASCOT5 that are published in each year. Our Slack channel has something like 150 members, but not everyone is active user. Some are like students that have graduated, but they're still there. And it's used both by physicists and engineers. And our aim is to become something like an industry standard code now that actually fusion industry is developing, and it's no longer just a like purely scientific endeavor. And the developer team, it's basically me, and then we have some other help like from Mathieu, and some users are contributing, but basically I would say there are like 3 or 4 active developers at the moment, and none of them are full-time working on the ASCOT development, because I'm a physicist, I'm looking at the physics problem, and ASCOT is more like a side project. And yeah, the applications, what actually ASCOT outputs, this is just like from the publications from the past 4 months, maybe this winter. So one is the wall load. So you have these energetic particles that are generated from produced in the fusion or used to heat the plasma, and their confinement is important. And one reason is that they are sensible to the magnetic field perturbation, and if they are lost, they can generate hotspots on the wall, and this can damage the reactor components. So ASCOT is a tool that is used to check that this doesn't happen, so that you don't get this unfortunate incident in your expensive machine. And then more physics-wise, ASCOT is used to calculate the distribution function, because that is essentially why ASCOT is tracing these particles to calculate this distribution function. And then third main topic that ASCOT is doing is to model synthetic diagnostics. So you know where you can put your diagnostics and what kind of signal you expect in an experiment. And I just wanted to put one slide showing equation because it's a physics code. Don't worry, you don't have to learn these. There are just a few things that I would like to point out here. ASCOT can be run in two modes. So one is the full gyro motion, where you trace this whole gyrating particles. But because it involves this fast gyro motion, but most of the time that is not of interest. But it's the slower motion of the center of the gyration. And this is the guiding center. So you can also trace this guiding center. But in your exercise, you will be tracing the full gyro motion because the guiding center, it is already ported to GPU, but not yet merged to the main branch. So only this full gyro motion has been merged. So that's why you are using that. And yeah, so let's get back to the performance part. So these equations, they assume that there are no self-interactions. So the particle markers are not interacting with themselves, and they are not interacting with the background plasma. And this means that we can run each marker independently, basically. So what we are doing in ASCOT to increase the performance is to just run as many markers in parallel as possible. So let's go back to the parallelization in ASCOT5. So I'm first covering what we are doing for CPU because what is done for the GPU is very similar. So initially we have this, here's this schematic. So this flow here is illustrating the flow of your marker population that you are simulating. So initially what you have is that these markers are just equally distributed to different MPI processes. And the MPI processes, after the distribution has been done, they don't communicate each other until at the end of the simulation when we collect the results back together. But during the simulation time, there is no MPI communication at all. So it's a very light MPI code. And then within each MPI process, we spawn threads. And these threads then take markers from this common queue. So we have some kind of load balancing in the code because these markers, they are not, their simulation time might differ. So we need to have some kind of load balancing. So we are doing load balancing inside MPI process, but not between the processes. And then finally, we have these SIMD vectors or the SIMD structures. So we make use of the SIMD instructions to then calculate this or advance these markers within each thread simultaneously using the SIMD instructions. And once marker has finished simulation within the SIMD vector, it is pulled from it and put back to the finished markers queue, and then new marker is retrieved from the unfinished marker queues and put that in its place, and then the simulation proceeds. And it's implemented with the OpenMP. So here we have the pragmas showing that after the initialization, we just run spawn the threads, and then we have these SIMD loops where the vectorization happens. So this is how the CPU part is done. And then for the GPU body strategy, to make things simple, we use the same version of the code, or try to have basically same code running for both CPUs and GPUs. And how is that done is that we use the OpenMP or OpenACC for the GPU porting, and we just define these custom pragmas or macros. So for example here, this loop, so for the GPU, if this is compiled using OpenMP, we have the same pragma, but it's just converted to this pragma. And for the OpenACC, it's converted to OpenACC pragma. And if it's not converted for the GPU, but CPU, then we have the OpenMP or SIMD pragma. So this, depending on where it is compiled, depends on how the loop is executed. And for the GPU, again, I have this flow here. So again, we divide the markers between MPI processes, and then there is no communication between the process after that until the end of the simulation, and then the GPU threads are spawned. And this is like the event-based approach, so that every time that in the CPU code we had these open simp loops, there we instead have the GPU loops. So at the beginning of the simulation, we offload all the input data, including markers, to the GPU, and then we just push the markers in the GPU, and then the code is advanced in the CPU until we push the markers again on the GPU. And then at the end, we just offload them back to the CPU. And then here's the benchmark. So this is a very physics-based or physical situation, except that the simulation time was short, but otherwise it's a typical application of ASCOT. And then there is this publication by Mathieu, if you are interested in that one, where this code was benchmark. And the benchmark is with respect to Ice Lake CPU and then the different GPUs shown here. And ASCOT, ideally, it should show like a perfect balance. So in the tasks, you are asked to show what kind of scaling you get. So you should get quite good scaling with ASCOT. So I don't have anything about this. Mathieu, do you want to say anything, or did I miss anything?
Thank you, Konsta. No, perfect. Just mentioning that, as you can see, in this figure, we can show the portability of the code across different architectures, and in particular across different GPU architectures. So in this competition, you will use only NVIDIA GPUs, but just to let you know that it can be used across different architectures.
Yeah, thanks. Then your test case and tasks. So this is so you're simulating an actual fusion experiment that will be hopefully executed in the next year, and hopefully it will actually achieve some fusion power. And the data that you will be using is actual data. It's shared in Zenodo, and except for the wall model, so you have simple wall, so which is a bit dull, but you cannot have everything. And so in this, we are producing 140 megawatts of fusion power, and 1/5 of the energy is released in the form of these energetic alpha particles, which is just helium, the same helium that you put in the balloons. And these helium ions, they have to be confined because, first of all, they are energetic, and then they collide with the background plasma, so they heat the plasma, so they keep the plasma heated, and this is important so that we don't have to rely completely on the external heating. And then the other reason was that if these energetic ions are lost, then they might generate these localized hotspots on the wall, which could cause damage or erosion in the wall, and we don't want to have that. And this, even though we are using actual data, this is not a full-blown ASCOT simulation, but a little bit simplified, because we usually ASCOT simulations, they take around like 10 or 20 nodes and consume like 1 day or something like that, and we don't want to do that for this competition. So I made some assumptions and changes so that we can run the simulation in short time. So I think they should take around 30 minutes or something, but with using the inputs that you have. So we are only simulating the alpha particles that are close to the plasma edge, which are more prone to the loss, and we are only simulating them for a few orbits and without collisions, because some of those are lost collisionlessly, and that's actually most of the losses in the real experiment are going to originate this way. So even with this simplification, we get somewhat realistic results. And then what you should get is this. So because we are not including collisions, there is no randomness included. So you should get exactly these kind of results with your setup. So at the end of the log, once the simulation has finished, ASCOT prints the summary of results that shows that this many markers hit the end conditional simulation time limit, which means that they stayed confined for the amount of time that we are simulating them. And I mean physical time, not the wall time or the CPU time, but physical time, the particle time. And then how many markers hit the wall. And you should know about the markers. And then in the instructions, there is that instructions to show that how you can generate these two plots. So this is showing the cut of the machine, and then this black line is the wall, and these blue dots are the markers where they end up. We would hope that most of them would end up here in the bottom or in the top, or in the top, because these are so-called diverters that can withstand larger heat loads. But then you have also markers hitting the actual wall elements. But for that, then there is this other 3D plot that shows the inside of the machine. And as I said, this is a simplification of the actual wall. And this shows how the power load is distributed along the machine. But nothing dramatic here in these numbers using these simplifications that we have made. But you should get exactly these kind of results. And then some notes on the exercise. You only need to compile the ASCOT5 main to run the simulation. As I said, ASCOT has this interface to Python, but this is needed only if you want for producing these plots and changing the marker input. But to run the code, you only need to have this binary. And you need to compile that binary separately for the GPU and for the CPU. But the wiki page has instructions for that. And in one of the tasks, you need to change the marker input. And this marker input, I just noticed that for some reason it had disappeared from the wiki, so we'll need to add it there back again. But here is the instructions that how you can do it in the Python. But this post-processing and changing marker input, you can do it either in the cluster, or you can do it even on your laptop, where you can install ASCOT using Konsta. It's a simple process. For that, the instructions are in the ASCOT documentation. And just one note about the input and output. So everything is stored, the input is stored in the same HCF5 file where the output is going to be written. And ASCOT can support multiple outputs. But this is not taken into account in the instructions. So what you should do is that always maintain or have this one clean input that you haven't run, and then make a copy and then run it. And if you're happy with the results, that's good for you. But if you're not, don't run the same input, but make a fresh copy again, because otherwise the instructions in the wiki, the post-processing instructions, they don't work exactly like that. Yeah. And then here are the tasks. So basically in the first task, just show the scaling for the GPU nodes. And then in the second task, so the scaling for the CPU nodes. You can play with the number of MPA ranks and OpenMP, so that if those would affect the results, because it's a hybrid code. And then for the GPU, you compare the 1 million marker input with the 5 million marker input using 4 GPUs and show your results. And then you can run profiler on the code and then visualize these results that you gained. So the scaling and so on. So these are your tasks. So I'm going to stop here, and I think now you can ask questions if you have any. And thank you for your time.
Okay, thank you, Konsta. It's open for questions. Any questions? Just you can say it or write in the chat. And yeah, Tobias is asking here.
Hi, I have a question for the in-person competition. Is it also guaranteed there that we will only use the simulation mode which is ported to the GPUs, or should we also prepare for tasks that run on CPUs only?
So we haven't finalized the task for the in-person, but we plan to have the ASCOT5 there for CPU or GPU, whatever cluster you bring. So whatever, I don't know what cluster you bring. If you have the GPUs, you can use them for the task. We won't tell you how to run it.
But if I understood it right, there are 4 simulation modes and only one is currently ported to GPUs in the main branch of the repo. So theoretically, if the inputs want simulation mode 2, then we would have to either use the other branch or would just be able to use CPUs.
Also, do you want to comment here? What I'm saying is just wait a bit, and then we'll until we'll finalize the task, and then we can discuss it internally. Konsta, you want to comment, or Mathieu?
So did you ask about the
in-person part?
No, but what was the part about the branches? Could you repeat that?
So the question is, should we prepare to have to use the simulation mode that is not ported to the GPUs?
No. We are using only the one that is already ported to the GPUs. Yeah.
Okay. Thank you.
And yeah, you don't have to change the options in any way. Only this marker input is that you are asked to change.
Maybe a follow-up question. For this paper that you showed earlier, I've looked at it and I cannot find the instructions on how to generate the data that was, or the input files that were used for those benchmarks myself, and I would like to reproduce that to ensure that everything is working correctly for our hardware. Can you provide the input somehow to us?
You can ask Mathieu to provide those. These are completely analytical inputs. So if Mathieu still has them, you can produce them. But you can also, well, if you want to do that, yeah, then ask for Mathieu.
Yes, I can provide this input. I have still the input used for the paper. I don't know how I can do that. Maybe in the same directory as for the in the mentioned in the wiki, for instance. I can put this input there, but I don't know if it is a good way to do that. Ophir, do you?
Yeah, we are part of the in-person competition, so I don't think we have access to that.
Okay.
It should be a small file for any matter, because it has 2D field.
Yeah. So, but not by mail. I can do that by mail because it's more than because it's 10 million markers, so it's more than 10 or 100, more than 10 megabytes. Huh?
What is the issue? You want to access with an input file?
Yeah, how to share the input file for this test case on the shown in the slide here. It is a test case. I ran it for a previous paper last year. So I'm
you
looking
put it on a drive or something.
Yeah, I will find some. Yeah, and I put the link. Then I will put it on a drive, and I share with you the link if you want. Can do that.
Okay, thank you very much.
Okay.
You're welcome.
There's another question here about some markers that are not exactly the same, GPU and CPU.
Yeah, I already answered in the chat. So yeah, they
should be exactly the same.
Yeah, there shouldn't be any random component involved. So it probably doesn't matter for the scaling exercises or anything, but as I said, they should be exactly the same. So it's a fun thing if they're not.
Okay. Anyone? Any more questions? Yes, Tobias.
Another question regarding tuning. Is it possible or advisable to use compiler flags that can affect the precision? For example, something like fast math flags, or should we not do that?
For the performance, yes, you can tune these flags because, in particular, for GPU, using O2 or 3 or fast can have a very large impact on performance. So you can tune that. I think at the end you will get same results like Konsta showed just before. But in terms of performance, you can have yes, you can have a large, big impact on the performance playing with these flags.
Okay, so also OFast is fine for this code and does not degrade the results.
No, you can use it. Yeah, you can play with all these flags.
Okay. So just a reminder, if you have any questions, you might be overwhelmed in the beginning, but any more questions, just don't hesitate, don't get stuck, and ask us in the Slack, either in the team channel or in the general channel, and we'll try to help. Okay.
Yep.
Okay, so I think we have another question. Samuel, okay, go ahead.
Oh yes, I have a question about the paper. I have searched on the internet and see a paper is called GPU protein of ASCOT5 code for Monte Carlo simulation in fusion plasmas. And I see you are the author of this paper, and I want to know. I think there be a new algorithm about the GPU protein, and it's about packing. Yeah, if event based and packing, and I don't see any relative code in the latest ASCOT5 repo. So it's normal or yeah?
Yes. So for the paper, there are 3 different algorithms. We compared the 3 different algorithms. In the main branch, so the branch we are using, we will use, there is only the event-based approach because there is another branch using packing, but this branch is not merged into the main branch. So it's normal to see in the main branch only the event-based approach for GPU.
Okay,
in the future, maybe in the future it's a possibility to merge the packing option, but not for the moment.
So it means I can find the packing algorithm implement in a specific branch, right?
Yes.
Okay, I will find it.
Yeah, you can find it, but this branch is not at the same level in terms of it's a branch created 1 year ago, and we have to update it. So maybe it can be difficult to compare to the main branch. But yes,
okay,
you can find this branch in the GitHub repository.
Okay, thank you so much.
You're welcome.
Okay. Okay, so what I suggest is that if you have any more questions, just use our Slack, competition Slack, and ask us. We'll try to help. Okay, and I would like to thank Konsta and Mathieu for a great presentation. Okay, and good luck, everyone. Okay.
I'm sorry. Can I ask a question before?
Yeah, go ahead. Go ahead. Before we close.
Yeah, thank you. What is the expected simulation time of a serial code of 1 million markers? The input file that you have uploaded to the website. I mean, without any parallelization.
I would say a lot. Do you have, Mathieu, any guess? But
alors, yes, we can extrapolate. I think it's 20 minutes or half an hour on a node, on a CPU node. So you have to multiply by, depending on the node, CPU node, but like 50. So 50 times 50, 100 times 20 minutes.
Oh, wow. Okay.
Yeah.
On a single core.
Okay. Yeah.
On a single
Okay.
core. Huh? Mm-hmm.
Yeah.
So without a PNMP thread, with one single PNMP thread and a single MPI.
Yeah. One MPI process, one thread.
Yeah, exactly.
Okay. Thank you so much.
An order of magnitude.
Sorry?
It's an order of magnitude.
Yeah.
It's not an exact timing.
Yeah. Thank you so much.
Welcome.
Okay, everyone. So we will meet in about half an hour for our things that we have the open form and the HimLB. Sorry. Let's see. So we have the HimLB in 9:30 Pacific time, and then after that, the open form. Okay, so we'll meet in about 35 minutes or so. Okay, again, thank you, Mathieu and Konsta, and we'll see you in about 35 minutes.
Yeah. Bye. Thank you.
Okay.
Thank you.
Bye-bye.